transdisciplinary research area is one of 6 at the University of Bonn, which all have the objective to pool expertise in specific strategic research areas at the university towards producing new knowledge, linking across faculties, and of course, promote excellence in research. Ours is specifically focusing on sustainability research, and we invite speakers to learn and establish new partnerships in this important field of sustainability research, which you all know involves many, many disciplines. That is why we sometimes have very broad lectures and sometimes also lectures that focus on one specific methodology or aspect or research field. Today, our guest, as I said, is Professor Xiaoxiang. She is a professor for signal processing and Earth observation at the Technical University of Munich. And she also heads the Department of Earth Observation Data Science at the German Aerospace Center, DLR. And she also serves as the director of the International Future Lab AI for EO, Artificial Intelligence for Earth Observation, as a co-spokeswoman of the Munich Data Science Research School, and she's also head of the Helmholtz Artificial Intelligence Research Field, Aeronautics, Space, and Transport. Xiaoxiang's research and the research in her group focuses on artificial intelligence and data science in Earth observation. She engages in developing innovative machine learning methods and big data analytics solutions to extract highly accurate large-scale geoinformation from large Earth observation data sets. Her team aims at tackling societal grand challenges such as global urbanization or the UN SDG goals and climate change. So she also works on scalable solutions for sustainable futures, which interests us here at this TRA. Last but not least, she has won numerous awards, one being the Leopoldina Early Career Award in 2018 and 2 ERC grants. This makes her a perfect fit for our lecture series. Xiaoxiang, we are looking forward to your presentation and the discussion, and for you to have a professional in the area to moderate the question and answers. You've seen it's not my field. We have invited Ribana Russia to moderate the question and answer session. But first, we're looking forward to your presentation now. Thank you so much for being with us.
Thanks a lot, Jan, for the introduction, for the invitation. I'm actually very happy to get connected with the Bonn colleagues. And today I will introduce our work on artificial intelligence and data science in Earth observation with the goal of helping shaping a sustainable future. I guess fits very well to this topic area. And since I'm told that not every participant is from the field of Earth observation, with this video, I would like to give a very high-level introduction to the topic. So in Earth observation, we are working with low Earth orbit satellites, and they are taking measurements of the Earth's surface. So while satellite is orbiting the Earth is also rotating. And in this fashion, we are able to get geoinformation of the Earth's surface on a global scale. And if the sensor would steer to a certain geographic region, then we can also get a very high resolution data. And the golden age. With this image, I'm not showing you how our PhD students are enjoying the lunch breaks. Even the working conditions with us is very nice, but not that nice. What I want to say is we're now living in the golden age of Earth observation because we have a lot of satellites orbiting the Earth and getting measurements. And this is a European view. Under the ESA, there is the Earth observation missions. At the moment, 25 under development and 15 in operation. The numbers is out of date. And it consists of 3 branches. Meteorology is more for weather services. Science branch is more for explorative missions. But the game changer is actually the Copernicus 9 with this Sentinel satellite fleet. And it basically provides global mapping with different sensors on a weekly basis. And what's more important is that it has open and free data policy. This means data from this satellite are actually accessible to everybody. And to give you a view, this is the data volume in the German Remote Sensing Data Archive. And today we are having around 30 petabytes of data. which will become 140 petabyte in 2030. And the larger part of this data are open and free. So that's why Earth observation is also becoming a big data problem. Where do we use this data in the context of towards a sustainable future? At DRR, we are research and develop solutions for major challenges in the following areas: Earth system research and environmental sciences, global change research, meteorology is a classic field we contribute to. We also deliver valuable geoinformation to support UN's sustainable development goals. And if we have very high resolution data, we are also working on very practical things like mobility, resource management, and city planning. So to show you some examples, this is the ozone concentration derived from the Sentinel 5P. And you know, this is our protection towards ultraviolet radiation. And you can use satellite nowadays to get a very nice daily monitoring. And this is another example, basically showing the NO2 concentration, also from Sentinel 5P before and during the Corona lockdown. So basically you will see the pollution has been reduced significantly during the lockdown. Okay, so why do we need AI and data science? So this is a system view of Earth observation. On the one hand, we have the observation system. These are our satellite making the measurements. On the other hand, we have the users. This could be, let's say, commercial users, scientists, or politicians, urban planner, whatever. And you can imagine what the satellite measures is not what the user would like to have. Therefore, we need information retriever to turn the Earth observation data to the geoinformation to serve different users. And that's why we need actually AI and data science here. In today's time, everybody who is working in Earth observation can easily confronted with petabytes of data. And in this context, the following area, the expertise from the following area are very important. Starting from explorative signal processing methods. This is more physical model-based information retrieval relies on our decadal domain expertise. Data fusion is another important topic because nowadays, if we work with Earth observation, for any applications, we will have data from multiple sensors. It's of course a wise idea to combine the complementary information from different sensors for a better application purposes. Information mining is important. With the big data, it would be really nice that we are able to figure out interesting data contains changes or interesting phenomena, preferably on an unsupervised or weakly supervised way. Machine learning, deep learning is of course a major topic because with the big data, we are more towards data-driven analytics for knowledge discovery or for different applications. And the last but not least, in order to be able to process petabytes of data, for example, for global change research, we definitely need big data management and high performance computing. And this is basically the areas my group is now focused on. And today, I rather try to tell two EO data science story instead of going to tiny details of many of these aspects. The first one is AI for EO. It's also called deep learning. In particular, I will talk about deep learning in remote sensing. As the eye catcher picture, I have borrowed the picture from ESA, where they took the satellite Sentinel-1 and then used a kind of style transform with AI methods to get a Van Gogh style for the image. And another topic is application on sustainability. And today, particularly, I will focus on our work on global urban mapping. So a bit educational aspect. So everybody has been talking about artificial intelligence, machine learning, and deep learning. This is how they are related to each other. But what I want to highlight is deep learning is the driver of today's breakthroughs in AI. And I guess, I mean, the wave of AI comes every 20 years. So 20 years ago, there is already the wave of neural networks, which has input layers, weighted, and there are also activation function. And finally, you get the output. This was known to be powerful. If you have two hidden layers of this kind of neural networks, basically you are able to model all kind of nonlinear processes. But then the AI winter came. This is most because if you want to really have such a powerful model, then yes, two layers, but it's very wide layers. At that time, because of the limitations in data training algorithms and also computing power, it was not possible to train. And exactly, actually, the advancement in these three areas brought today's high wave again with the deep neural networks, which in a very, let's say, in a sense, it's nothing different from the classic neural networks. It's only that you have much more layers compared to before. And of course, every day you see AI uses, most of the secret behind it is that there's a deep learning algorithm trained with a lot of data and with a lot of computing power. And because it's, let's say, performance, for example, in perception tasks and many other tasks, of course, it's also drawn attention of the people in the remote sensing community. And here basically is the literature overview, deep learning remote sensing from Scopus, starting from 2014, basically the beginning, and how it evolves. So basically you see this is not only a linear increase, rather exponential increase. And for 2020, already today in the database, which is known to be a lot of lag, it's already much more publications than last year. I suppose it will go actually with several hundreds more. So this is just showing you deep learning remote sensing is a super blooming field. And for us, actually the key to apply deep learning techniques in Earth observation is to think about what makes deep learning in Earth observation special. So this is incomplete line-up of the things we need to take care. For example, classification and detection problem, which is the main problem in computer vision, there are only actually a very small fraction of problems in Earth observation. Instead of that, we rather focus on the retrieval of physical and biochemical variables. And this means we need to have the traceability, reproducibility of the results. We should be able to quantify the quality of the measurements. And we also have decadal expert knowledge. Many of the things we don't have to learn from the data from scratch. And our data is also very much different from the internet images, which is used in the computer vision community. Instead, we have multimodal data, radar, LiDAR, super hyperspectral data, also unconventional data like GIS or citizen science, social media data. And when we talk about radar, then we're not talking about real numbered gray values. Instead, they are complex valued measurements. And on top of that, we don't have ImageNet, which has 14 million of images labeled to more than 1,000 classes. In our application, we are usually lack of sufficient training data. But the good thing is for our data, we are actually have very well controlled data quality, which is, for example, radiometrically, geometrically, spectrometrically, very well calibrated. And we know the statistics of the sensor. We even know the SNRs of the measurements. So these are the things which actually makes deep learning in Earth observation special. And based on this spirit, we have actually developed a lot of tailored deep learning approaches for observation problems. Here is just a small selection of the things we do. This is what we call the deep net zoom. I would like to show a few examples. So for example, hyperspectral image analysis. For those who is not from remote sensing, hyperspectral sensors, different from our RGB camera, it has hundreds of continuous band. And you can imagine different material will give different reflectance. Therefore, with these hundreds of bands, this materials has its own spectral signature. It's a kind of sensor which is very powerful in discriminating the materials in the scene. And of course, then one problem is for these layer bands, if they are very close to each other, then there is very redundant information for any kind of classification task. For example, it's very important to extract features from this type of data first before you go to kind of classification or other downstream applications. So this is an early work we did. It's unsupervised spectral spatial feature learning. And the idea is the input data, output data of the network is identical. And then it has kind of a convolutional or subnetwork as an encoder to reduce the size of the data to a kind of a bottleneck layer. And then you try to blow up it again as a decoder to reconstruct the image with the loss that you want to have the reconstructed image as close as to the input image as possible. So through this training process, you don't need labels, but the bottleneck layers, these are the features we could extract from the data. So this, of course, can support downstream applications like classification on the left, or because the rich spectral information we have, you can see the output from the very first layers of neurons already give you high level semantics, like the shapes of the buildings and also the vegetation. So, but in the hyperspectral world, one of the problems is the high intra-class variability caused by illumination condition, topology, and all possible reasons. For example, what you see, this is a hyperspectral data cube. If we select the area, which is trees, if you look at on the right, the spectral signature, you can see they are actually not identical, they're different. And here is just a video to show how you can use machine learning models to extract the features in a way that different classes of objects can very well distinguish from each other in the feature space. For example, you see this is the Sawyer spectral signature, which has a very large variability. And this is basically showing how they are finally get very well separated. And this is the three-dimensional visualization. If you go to higher dimensions, then you will see clear separation. But of course, this is not easy to visualize. The second example I bring is the time series data analysis. This is a super relevant topic in Earth observation because for Sentinels, basically, if you work with Sentinel-1 or Sentinel-2, you do any kind of application, you could easily get a time series data. This is an example we do with deep learning. And if you actually work with multi-temporal data, in this case, just to show the principle, we only took 2 time stamp. And it's a standard way for doing, for example, change detection, is that you first get a kind of convolutional layers to extract the from the data, and then you stack with kind of a recurrent unit. And finally, through the fully connected layer sigmoid or softmax, you will be able to get a binary change detection mask. This means change, no change, or multi-class change detection. And this is a visualization of the results, basically with the 3-year difference. In the middle, you get the change mask where you see a lot of city expansion. And on the right, you see which type of change is actually happening. It's more city expansion, soil change, or water change. And of course, you can, this is a general workflow. You can also work with multiple time series data. For example, this is the example of Munich airport. And you see upper part is the satellite imagery. Lower part is the multi-class, basically the change. And you see how the Munich airport has been slowly built over the years. And I'm also always making fun that probably after another 20 years, we can again use the satellite to prove the high engineering quality. And then you will see how where all the infrastructure are maintained. Okay, then one more example is global applications with the Sentinels. So if you work with Sentinel-2 data, I guess the first problem you will have is the cloud. And because 67% of the land cover you can expect clouds. So how to remove the clouds? So this is something we do with generative models. And basically in the classical methods, there are always assumption that clouds are only visible in the visible band, but not in infrared, and making this as kind of prior knowledge to remove cloud. Here is just a counter example. You see basically cloud everywhere. And the approach we take is that we take the cloudy optical data, which is affected by clouds, and add conditions, which is from radar. Radar can penetrate the clouds, therefore it's not affected by the clouds. But the geometric information is of course the same. And we're using the radar data as a condition to generate cloud-free Sentinel-2 imagery. And this is a real data example where you see cloudy Sentinel-2 input. This is the ground truth data, and here is what we generated. So from the visual appearance, it looks actually quite promising. And the last example is related to citizen science. So not only satellite is taking data. If you imagine the social media platform like Flickr, Twitter, they also deliver massive data. Most of them are basically shared under the Creative Commons license. This could be used as a complementary information for Earth observation, for geoinformation extraction. So we have been streaming 300 million tweets, which is precisely geolocated on a global scale. And for example, we are trying to do NLP through the, on the one hand, a spatial temporal distribution when the tweets are sent, plus topical modeling and linguistic feature analysis, which topics are discussed at different places. It can be used to, for example, for building type classification to distinguish where a residential and a commercial area. And remember, this data are actually globally available and are free to be used. And another thing we do is, during the COVID, there are also a lot of social media activities. What we did is we took all the tweets sent from Europe. This is, of course, a multilingual setup. This means you need to do multilingual embedding in order to basically be able to link different linguistic features. And then we do a sentiment analysis. So this is basically the average sentiment, how it evolves over time according to different countries. So basically you can see there is a clear dip after the first lockdown, which is announced. And you can also observe the whole community has been recovered very soon from this situation. And another interesting observation is that I don't know for which reasons, the general average sentiment score of Germany is relatively significantly lower than other European countries. Maybe we are too serious. I don't know. Yeah. So this is something we do with COVID. And the last example is more for fun example because I fear it's not good to end with a pandemic story. And please listen to this video. After that, I tell you how this is generated. I guess you can hear the sound of the satellite imagery, right? So basically.
No, we don't hear the sound. At least I don't.
Ah, okay. So there might be then problems with the audio. But what I want to say is here is what we did is we trained a model with pairs of in-situ audio and the satellite imagery, and we are generating basically plausible audio of every satellite image. So if you could hear, you will hear the sound of highway residential areas. You hear the laughing of kids. So it's actually a very, very, let's say, plausible, let's say, sound of the environment. And this is also something you could do with deep learning today. Well, so I guess with these few examples, I could convince you nowadays with deep learning, we're really doing already very well in all these kind of simple perception tasks like classification, segmentation, and so on. The big question is what comes next? So as the last part of the first story, I want to share with you our methodological research agenda. Because actually nowadays for the exploitation, what deep learning can do in Earth observation, there are a lot of things going on. But it's more still stay at the, let's say, trying phase to see what it can achieve. Yet the fundamental question remain open. Here is, for example, how to actually re-implant physics, space, and domain expertise with this kind of data-driven analysis. This is, of course, a very fundamental and important topic. Well, Ribala is also working on this. And another one is reasoning. So, I mean, it's very easy to figure out there is a car, there's a road, there's a building. But the network can still not get the sense. For example, our car is usually on a paved road, and street is usually in the cities nearby to the buildings. All these kind of relations, which is not included in the current model. Or to a more different example, today it is probably possible to map all the slums, but it's still not possible, for example, to combine hydrological models and the psychoeconomical models to figure out which part of people in the slums, they are vulnerable to sweet water supply, for example. These are more the reasoning topic. And another thing is transferability. And I mean, when we use machine learning for Earth observation, very often we have training data in developed areas, but we're actually interested in developing areas. So how could we make the model that can be generalized for different geographic regions? This is, of course, also a fundamental thing to work with. And then uncertainty. So today, with all the open tools, open data, to run a model, get a visual appealing results is very easy, I would say. But as Earth observation, we are doing measurements, not a vision task. Therefore, it's very important to be able to give an error bar to the measurements, how reliable this kind of predictions actually is. And then explainability. So we are from the classical physical-based education. We would not be happy to let a black box replace what the very sophisticated models we developed. Therefore, it's very important to make the model to be explainable. And this is also one way towards where you can insert actually domain knowledge to make the learning process more efficient or more accurate. And then a very practical thing, AutoML, deep topology learning. I was in the very beginning introduced, there are more than 3,000 papers of deep learning in remote sensing. I can promise to spend half of the time tuning the hyperparameters, how many layers, which kind of parameter, and so on. So therefore, it would be very important to figure out automatic way, basically find this kind of hyperparameters. And the next topic is quantum computing in AI. So ESA just announced the agenda of digital twin Earth. if we really want to have a digital twin of the complicated Earth system, then we definitely also need to work on the next generation of computing system. And here, quantum computing, quantum machine learning are very important. And the last part is ethics. I will have an example later. Then at this moment, I don't spend too much time on that. Yeah, so this is the open things from the methodological side. Well, my lab are focusing on. And of course, if you are interested in working on any of these problems, you always need a training data. Therefore, here I would also like to share 3 brand new data sets we prepared. They're really very large scale data sets and representative ones, I guess could definitely be a good starting point if you want to have your hands dirty on AI for your problems. The first one is the so-to-said LCZ42 datasets. It's for the classification of the global local climate zones. This is a classification schema from the urban climatology community, and it describes temperature, compactness of buildings, height of buildings, percentage of green. We are interested in this because we have a global urban mapping project. We are interested to have it as kind of morphological structure description of urban area. And in order to basically do a model that can scalable to a global application, the first thing we need is to build up a training data sets. Therefore, 15 scientists from my lab, we selected 42 cities across the globe, covering 10 culture zones. And then we are manually label them to one of these 17 classes showing above. And also because LCZ is rather a high level abstract description, because what is compact, what is open, these are the things different people have different opinion. Therefore, we consider it's very important to get confidence about the labeling. For this purpose, we let 10 experts to independently vote for these labels, such that you can also get a kind of label confidence. And this data, we make it open to everybody. Also, the baselines pre-trained models are available. And the key features, it has about 50 gigabyte, consisting of more than 400,000 pairs of Sentinel-1 and Sentinel-2 image patches with LCZ labels and the label confidence. And this is actually a suitable benchmark for quite some tasks like image classification, and data fusion if you're considering the fusion of sound and optical data, quantification of uncertainty if you're rather interested in the label confidence. And this is actually probably the unique data sets which you can get a label confidence. And this is definitely one option that you can get your hands dirty here. And another one is Sentinel-1 to MSCR data. And this is a large scale benchmark for cloud removal. And it consists of more than 100,000 triplets of dual pole Sentinel-1 data as the condition, and the clear sky multispectral Sentinel-2 image and the cloudy Sentinel-2 image. We did particular care to make sure the distribution of cloud percentage to be nice, where you can see here. And also the data are sampled globally from more than 160 locations selected from all seasons. And this is, of course, very precious data. One is more for those who don't want to dealing with too large data sets, but is interested in innovative applications. This is ERA, a benchmark for event recognition in aerial videos. Basically, it consists of nearly 3,000 aerial videos, which we labeled into 25 event classes. So this data, they are all open, and I think it's published all in this year, and you are welcome to have a look at them and basically do your own machine learning development on these data sets. Okay, this is a very quick tour to deep learning in remote sensing. And the second part is more related to sustainability. As I said, it's about our work on global urban mapping, which is funded in the framework of a ERC grant. And in the context of SDGs, of course, we are more look at the number 1, no poverty, and the number 11, sustainable cities and the communities. And the big background is we all know urbanization is a bigger trend, it's a mega trend. But if we look at the geographic distribution of urbanization, you will notice urban growth happens mostly in developing areas, let it be Africa, Asia, or South America. And for these regions, actually there's no appropriate geoinformation available. So for example, if urbanization is not controlled, it will end up with informal settlements. And of course, in order to somehow improve these informal settlements, you first need to have geoinformation like the building models, population distribution, and all these kind of things. Now, in the era of open science and open data, if I talk about building models, you probably will first think about OpenStreetMap, which is indeed the biggest open data platform for urban. And here is the state of the art. In the world, there are more than 3 billion buildings, and only about more than 300 million buildings that have a 2-dimensional footprints, which is the shapes of the building in OpenStreetMap. This is less than 12%. And among these, only 3% buildings have height information with big errors. So this is then about 0.5% of the whole building. So we are using AI data science association to close this gap. So the first thing is to get the global building footprint. And the number 1 task is to figure out appropriate sensor. And in this project, we're using the NewSpace data from Planet Lab. So they have more than 140 these stoves as held by a real hand, small satellite. And the power of this constellation is that they can provide a daily coverage of the Earth's surface with 4 bands with a resolution 3 to 4 meters. And the approach we take is that we build up a training data sets. These are pairs of satellite image on the left, plus the corresponding building footprint taken from the GIS data selected from 74 cities. Then we have trained a graph convolutional recurrent neural network. And on a high level to explain, for the graph part, it's more to get the large contextual information. For the convolutional part, it's more to get the high level spectral spatial features. And for the recurrent unit, it's used to progressively improve the segmentation results. And now we train the model and we processed the whole Africa. And today in our data, for Lagos, for example, this is the input data. Lagos is a city, by the way, with more than 21 million population. And for such a city, there's no actually open city maps, city models available. And through our model, we produce a building footprint like this. If you look at a zoom in area, this is the data, input data we use. You can see 3-4 meter data. It's the best spatial resolution we can get on a global scale as today. But this is also really already the limit. So in order to get individual building information, this is the minimum required spatial details we need to have. And this is the building footprint we get from our model. And if we add also multitask learning, then we can also get the building instance, which means which pixels of the image are belonging to the same building. Here, different colors stands for different buildings. And here you already see the invitation of today's data and the technology. These are slum areas. They are too packed together and the similar height, similar appearance. Basically, the best model of today cannot tell individual buildings from this kind of slums with 3-4 meter resolution data. And of course, if you have multi-stamps of this data, you can also do change detection. And here is another example. You know, in August in Beirut, there is a tragedy happening, this explosion. And what we did is we take a planetary imagery before the tragedy and after the tragedy, and run this through our pipeline, and we get the building footprint extracted. And by directly compare these results, we will get a damage mask of the buildings. So this is on the one hand, validation, the generalizability of our model. On the other hand, it's also a way how you can actually use this kind of technique for different applications. Okay, so far we are talking about 2D. And how about mapping every building in 3D? And this is the approach we take. So we are using the German TANX data, which is globally available, but the number of images is quite limited. Then we are using more model-based methods. We call X-ray of the Earth. You can imagine radar works like a CT. One image could be a tomographic slide. We take slides from different positions and try to do a tomographic reconstruction. And with this model, we are able to get the building height. And then we combine with the building shapes we reconstructed with deep learning. And I'm now able to show you the first impression of the global 3D urban models we are about to get in 2022. And this is Munich. And the color stands for the terrain height plus building height. And we have compared it to a very precise LiDAR DEM with more than 30,000 buildings. And we end up with building height accuracy better than 2 meters. And in 2 years, all African cities would also have this kind of information. And such a model, I mean, for German cities, probably is not so added value, but for African cities where they don't have such information, this is of course a great benefit. And so far it's about morphology. How about understanding semantics? And today in the whole project, we want to get the building function, classification, commercial, residential, industry building, and so on. Today, I'd rather give an example of slums. So if we talk about sustainability, global south, this is of course the regions we should pay particular attention to. And when we talk about basically segment out slums, one challenge is that at the different geographic regions, the appearance of slums are totally different. For example, this is in Caracas, and the slums actually look like this kind of high story buildings. And if we look at Mumbai, and this is actually this kind of blue roof low buildings, but it's not probably with lightweight material. And if we go to Nairobi, and this is brown roof lightweight buildings, this is how it looks like. So if we want to get a model that can work on a large scale, the first thing is that we need to get a representative training data sets, include all possible variant of appearance of slums. That's why we have selected 10 cities from the global south and build up a large scale poverty data sets consisting of more than 4,000 slums, total slum area more than 200 kilometers square. And with this data available, then you can actually use any backbone segmentation network for doing so. And here, the lesson we learned is in order to get a good accuracy, it's better that you train a general model, then try to fine tune according to certain geographic regions to have it more, let's say, robust for different areas. And basically, you can see for different morphology, Caracas, this is the results. We get a F1 score more than 86%. And this is Mumbai with F1 score close to 87%. And this is Nairobi, and the F1 score is more than 83%. And this is basically, we see, we get a quite good results everywhere. And now we are working on extend the whole pipeline and try to really get slums on a global scale. Yeah, this is the examples I would like to show today, but the whole project actually go far beyond this. We are actually turning 10 petabytes data from Sentinel-1, Sentinel-2 planet, 10x all possible sensors. Also social media data, which are tweets and the Flickr imagery. And we want to get global buildings in 3D, I showed already. Settlement types, today I only showed slums. Morphological structure, population density, and the evolution over time. And yeah, so this is the global urban mapping project. And we will make all this data open and free access to the community. And on the one hand, we want to lead the community to have data for a better understanding of urbanization. On the other hand, we believe such a data set is, of course, super relevant for stakeholders like UN for the strategical decisions. Yeah, so this is basically the second data science story I want to tell. And the last part, I will take 5 minutes to introduce you some of the initiatives we have in the Munich region. Actually, through the last 6 years experience, we figured out the most precious resource in AI for EO are actually the high potentials. And if we talk about AI and data science, we are basically in direct competition with Amazon, Google, which offers a very fat salary. We basically encounter the situation we need to educate our own data science who are engaged enough with our domain. Based on this spirit, we have been working intensively on different initiatives in order to somehow manage to get a gravity center effect for AI, for EO to attract young talents. And this is basically initiatives we have. For example, Helmholtz-wide, we are having the Helmholtz AI, which is a German-wide AI initiative. The idea is to get a hub of the data science AI expertise in Helmholtz to promote its application in the 6 research areas of Helmholtz. And here we are getting a local unit, which is more for aerospace and transport, which is with us in Oberpfaffenhofen. And we are more actually have experts from Earth observation and robotics served there. And we have built up our own school of data science exactly in order to train our own data scientists. This school is a collaboration of domains with computer science colleagues. It has a very interesting model. Every PhD student shall be trained by 2 PIs, one from computer science, hardcore data science, machine learning, another one from the domain. And in this way, we make sure that the PhD student get the best from the 2 worlds. And on top of that, actually, 3 days ago, announced by TUM, we are establishing the Munich Data Science Institute, which should serve as a kind of hub of all data science activities in the Munich environment. And here we are also putting Earth observation as a very important domain. And myself is also serving in the board of directors here. And also a month ago in Munich, we established ALICE unit. ALICE is a European-wide elite network for machine learning and AI. And for the Munich unit, we have 4 focus areas at the moment, which is, of course, machine learning, but also computer vision, biomedicine, and Earth observation. And you can see we basically try to get all possible connections with Earth observation as a domain. This is basically a must in order to be able to get a nice kind of hub to attract young talents in the very competitive AI and the data science field. And the last one I have not introduced because I want to talk a little bit in more detail, 2 or 3 minutes, is the International AI Lab AI for EO, where Jan mentioned already in the beginning. And this is basically one of the 3 BMBF funded international AI labs. I'm very proud that we have one of them focus on the topic of Earth observation. This, I guess, is a milestone to establish Earth observation as an important applied AI field. And the idea is that we will bring 13 guest professors from everywhere and also 70 young talents to Munich and work on 3 fundamental problems, which is reasoning, uncertainty, I talked about before, but also ethics. And why the ethic topic? I mean, for reasoning, uncertainty, I explained already before. So this is an experiment on Twitter. So someone uploaded 2 of these images and want to see which will the tweet algorithm pick. And this is basically turned out. So in both cases, it picked up the white faces. Obviously, this is because in the machine learning algorithm, there's a data bias. There's too many training samples of faces from the white people. And this is the well-known data bias problem. But this is also actually a relevant problem in Earth observation. Because, for example, if we do a machine learning project for developing areas, very often we only have training data from the developing world, developed world. There is, of course, a certain bias in the data. And then, for example, another example is now with data science and also EO data, we are making a lot of non-existing geoinformation available and make them public. Would this then be misused? All these kind of issues are really future topic. That's why we also put ethics in AI as an important topic. And this is in complete line of up of people who are involved. And basically our goal is really to make progress in these 3 fields. And why I'm talking about this, because actually we are now looking for 70 Beyond fellows to join the lab. What we offer is 3 to 6 months funded research stay in our lab, and based on solely on the criteria that you should have an innovative AI for your topic. On the other hand, you should be a talented individual. So this, I guess, is really a great opportunity to get connected with international expert. And if you student or yourself are interested, you are definitely welcome to be in contact with us. And with this, I would like to conclude my talk. And with 30 minutes, I definitely will not be able to go to all details or all projects. But if you are generally interested in our activities on global mapping or AI for you, you're welcome to visit our website or write me an email if you have further questions. Thank you.
Yeah, thanks a lot, Xiaoxiang, for the interesting talk. I think it's super exciting to work at the moment in remote sensing and data science. And okay, now the floor is open for questions.
Thank you for a fascinating talk. So much exciting and new insights. I have a rather specific question about cloud removal. I'd be interested in air pollution and the sources of air pollution and the distribution, and to connect that to health data. So I'm interested in partial cloud removal and the maintenance and visibility of polluted air. Where do we stand in on that research with remote sensing? So where the pollution is, where it comes from, and where it goes to.
Yeah, I would say cloud removal is more meant for, let's say, optical data analysis. Well, clouds serve as kind of nuisance area that you cannot see through. For the air quality monitoring, then we're actually more using the spectrometers, like on Sentinel 5 or so, that you could basically record let's say, the sun radiation through the atmosphere, what you received, and you can try to get the gas concentrations through the radiative transfer models. So these are 2 different, let's say, separated tasks. And when we talk about cloud removal, we really meant to implement kind of data to fill in the gap. I hope this explains clear.
Yeah. Okay, thank you. Jürgen, you're next.
Thank you for your excellent presentation. Jürgen Kusche from the Institute of Geodesy here. So my question would be related to the challenges that you mentioned, like explainability, representing uncertainty, also including physical knowledge, or in general, what you call domain knowledge. I mean, when we model the Earth system, we have lots of coupled models, simulation codes. We are pretty good in describing, for instance, atmospheric circulation, ocean circulation, atmospheric chemistry, for instance, maybe not cloud coverage. This is maybe the exception. And we also have tools that represent uncertainty and that are able to integrate data. I'm talking about data assimilation in models, in Earth system models. So my question is, where do we stand in connecting deep learning and data assimilation?
Yeah, this is a super great question. Actually, I would say it's relatively open field. Maybe you have heard about there is a ERC synergy grant from the MPI in Jena, DIR Atmospheric Physics Institute, and also from Valencia. Also somebody from Colombia. They're basically trying to get a first clue how deep learning could be married with the hardcore model-based approach. I would say there is, of course, a lot of potential when it comes to understand the causality in the process, when you try to basically to get a reliable long-term predictions by combining data, machine learning and the models. But I don't think we are there already now. It's rather in the phase, it's taking off. It definitely needs much more brilliant minds for this topic.
So we are not there. We have to wait 5 years or 10 years or?
Yeah, I mean, I can only share ESA has a big initiative, which is called Digital Twin Earth, works exactly on the area of to combine AI, EO data, and Earth system modeling. They are aiming at get a breakthrough in 3 years. But personally, I doubt because it took much longer, in my opinion.
Thank you.
Yeah, thank you. I agree. I think if we solve the first task and combining data assimilation and data science, that will open up new questions, and then it's a promising direction. I totally agree. Okay, so the next question is from Nadi.
I was just saying that I'm coming from a junior researcher question, so it's a bit different question. I am just basic user of GIS and remote sensing using different indexes to study the dynamics of wetlands habitat. And before I hear this presentation, I was so proud of my work using different indexes. And now I would say that I'm really excited and maybe depressed a bit because I feel like I'm lacking behind. So I have a question for you. What do you recommend a researcher to transform from using like the very basic knowledge of remote sensing using different indexes to start using deep learning in understanding habitat change and ecosystem service analysis and so on? What is your recommendation here? Thank you so much.
I mean, I don't think your approach is not, let's say, valid or exciting, but certainly nowadays with available sensors, big data, and new technology, there are a lot of new insight and geoinformation are becoming available. So I guess, I mean, instead of rely on the indices you have achieved probably with well-established methods, And but of course, you will have probably large scale available data. You could try to embrace basically the improvement we are now let's say accomplishing with all these new developments. Before that, maybe it's even better to discuss your field rather in a more interdisciplinary environment, because you know, I guess you will need besides you expert from the machine learning side, expert from let's say big data analytics of Earth observation data side, and to do some kind of brainstorming. And this might lead to probably the next step of which ways Earth observation could interact in your ecology related study. So I mean, I know it's a very kind of general recommendation, but from my previous experience is that it's always tricky to approach a certain problem from just one angle. Then in the end, for example, I can give you my personal experience. I had this ambitious global urban mapping project. Of course, through the way, I'm trying to push the limit what today's technology can actually achieve. And there are a lot of challenges when it comes to the level of detail of information, big data processing, and so on. And after a while, when I present my results, then the urban scientists tell me, okay, I could have already be satisfied if you could simply do much simpler things. So I mean, there is definitely gaps in different disciplines, even though it's a general suggestion, but I guess this is the best suggestion I can give based on my previous, let's say, projects and experience.
Thank you so much.
Yeah, thank you. So there's another question from Hugo Storm. Please go ahead.
Yeah, thanks a lot for the very interesting presentation. So I have a question to working with these hyperspectral images and your DeepNet zoo. So as I understood, one of the challenges with these hyperspectral images is that you cannot really use these pre-trained classical image processing networks. So the possibilities for transfer learning are much or not really given. So my question would be, are these your DeepNet zoo, is that available, and would that be possible to use these in a similar way for transfer learning as is done with these ISNet, VGG nets in typical image classification, image processing tasks?
Yeah, sure. So actually, for most of the work I presented, we have the code also available on our website. If you go to the last page, you can get access. And actually, in the context of hyperspectral image analysis, I showed you the work we did with this unsupervised feature extraction. We have also been working with recurrent models to model spectral signatures as kind of a sequential data. We also did enforcement learning in order to automatically decide which bands are important for different data adaptive selection of bands for different regions and applications. And all these kind of things, you can have a look at our website to get access to the codes.
Yeah, thank you. I think that's really valuable for the community because this is not the usual case for the remote sensing community. Okay, I'm not sure if there's one Alfariani. I don't know if you have a question because you, there's a in the participants.
No, sorry, I was fiddling with my phone.
Okay, fine. Maybe then I have a question. So there's one direction in the computer vision community. I realized that regarding to multitask learning, so they try not to learn specific models. They try to learn one model to do everything, like sentiment analysis, image segmentation, everything what you can imagine. And you mentioned something I think when you talked about in transfer learning that you want to learn a general model for a specific region. So I would like to hear your opinion on what do you think? Should we go for specific models for a specific application or learn more general models which might be not so accurate?
Yeah, I mean, the answer, the universal answer, it depends, but it's really the case. So if we are really talking about general properties of, for example, what I did with urban morphology, it's compactness, height, these kind of things that can be generally described. Then of course, it's better to have one general model which can work well everywhere. However, if it's really for us, of course, geographic regions is important. If it's really very culture dependent stuff like building functions or these kind of things, I don't believe there will be a general model that can work everywhere. You can only rely on relatively larger and representative data sets to get a good pre-trained model. And if you go to any kind of geographic region you want to look at, it's always more recommended to add some samples from there, try to fine tune your model such that you can get a good performance at these regions, of course. Yeah, but of course, I'm also a fan of multitask learning, but only if these tasks are really supporting each other. For example, if we are trying to get buildings, then it makes sense to get a segmentation task and the boundary kind of detection task together. And if we are basically doing related, for example, land use, land cover classification task, one time let it to be urban morphology, the other one let it to be semantics, then they also relate to each other. I mean, multitask learning only makes sense for me if they can more or less have a kind of clue for each other in a way that the joint learning is better than individual learning, so to say.
Yeah, exactly. I mean, I always hope that we can overcome maybe a little bit that we do not need so much training data for each specific task, which is so hard to get. Yeah, interesting, exciting. Okay, I can see no further questions. So I would say last chance to ask. If not, I suggest to give over again to Jan.
Thanks, Rebana. Thanks, everyone. I don't want to extend this too much longer. I just thought that this was a very nice complementary presentation to what we heard a few weeks ago. Now, especially with examples on urban mapping, and I think this will really inspire us in terms of thinking how we can, especially me as a social scientist, how we can use more of what you produce in our work. I assume it will inspire the other remote sensing scientists in this room in a very different way. But this is actually what we want from this lecture, right? That we find out how we can all benefit from one discipline or from one certain innovation activity in a certain area. And in that sense, I really loved hearing your presentation today. And I hope we can be in touch, especially with all your interesting initiatives that are ongoing, and maybe explore future areas of collaboration. As we said in the beginning, the meeting will be recorded, so we'll make it available also to those who weren't able to participate today. And I hope we can meet again very soon, early December, in our next lecture series with Matthew McCabe. And I hope you enjoyed the lecture. Thanks once again, Professor Xiaoxiang for making time. And thank you everyone else in the room for being with us. See you soon. Bye-bye.